needs to be in. All right, get me started, model. Solid calcium oxide is added to what? Get me started. CaO solid plus, I'm going to write it as HOH. Would that be helpful for this one? Maybe. Okay, and I'm going to show you guys why, okay? All right, give me a prediction of the product, Megan. Okay, this is calcium hydroxide, right? So metal oxides plus water always make metal hydroxides. Metal oxides plus water make metal hydroxides. The way you can see that, though, is calcium ion can get with hydroxide, right? But then what's left over? Hydrogen, oxygen, right? But we can't make anything with just those. So it actually comes in as the secondary hydroxide that calcium hydroxide needs to make a neutral compound. Because when you form calcium hydroxide, it's not CaOH, is it? 2. So that first calcium and hydroxide come together, and then this little extra OH is the second OH that's in a compound. Do you see it? It might help you just understand how this is coming to be. So I know that this is somewhat insoluble, right? So we call it slightly soluble, but that does dissolve ionizes. That of which does dissolve with calcium hydroxide will ionize, right? So because it's a strong base. So we're going to go ahead and let's actually just balance first. Yeah, it is. Okay. From there, write your NIE. Does this change? This one? No. Does this change? No. And I saw some of you guys ionizing water on your NIEs in your non-solutions lab. No, 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 no. It ionizes so unappreciably, we just ignore the fact that it can even do that unless we're specifically doing pH stuff, which we do have to think about. This is our pure liquid still, and this, when it ionizes in its strong base form, will make calcium 2+ and 2 hydroxides. And I say this because occasionally we'll have things that form slightly soluble products, so we have to think about, like, can I form the NIE, or do I leave it as a solid precipitate? Sometimes there's not exactly a right answer, which is why I have to be flexible with you, but it will give you some leeway in terms of how to approach the answer. So I could ask you a question here, other than what's the closed solution. I could say, what forms if the conductivity of the solution increases? Well, it wouldn't be a solid, would it? Because that wouldn't give you any conductivity. So if I said, what forms if the conductivity increases, you think must be ions separated into 2 ions, which gives you a little help to get to the final product here. And these, of course, would be aqueous. You don't always have to write the states of matter. Sometimes it's a waste of your time, but sometimes it's really helpful if you're writing the NIE out. Okay, the color of the solution, anybody? Take a guess.
Green.
Don't get crazy on me. Hold up. It's white, right? The things that we formed last in our precipitates lab, everything was white and clear. So if you want to say anything, you can say it's a white clear solution. Because the white part is the part that's slightly soluble, right? That's somewhat giving you a little bit of a hazy precipitate. And the clearish part is the ionization that's forming. Okay. Next. And this is, just note to self, this is how your questions will be asked on your pre-response part of your test. I just finished making it, I diminished it in questions just a little bit so we could finish in time. It's 5, okay, from the top of my head, 5 NIEs. Okay, which can be like these right here in terms of, not all are aqueous, so don't think you have to ionize them all. 1 ion concentration question, like BEA style ion concentrations again. 1 titration question, I might be lying to you, it might be 2, with particulate drawings, which we're going to practice today. A lab-based, they call it gravimetric analysis, but lab-based math precipitate question. One of those. I'm missing something. Can't remember. Okay, but 25 multiple choice questions, but 6 are math heavy, meaning mental math heavy, meaning we're going to practice some more of those. Your test is next Tuesday, by the way, but we're basically doing labs the rest of this week. So I just want to make sure that you're clear that you can start studying now. We're almost done covering all the curriculum for the unit 2, but we don't test for another week and some change. Okay, I can think of some more there. Some of those multiple choice, of course, are going to be organic, which is the part that you guys are doing on your own. Okay, back to me. Liquid pentane. Formula? C5H12, so that's the 2N plus 2, 5 carbons, 2N, 10 plus 2 is 12. and that's because it's an ane. Okay, burnt in air means what? O2, so it's combustion, right? So CO2 and water. You do not have to list the states of matter over here if you don't want to. It's just sometimes helpful for people to understand we're not going to ionize things. Will you ionize anything here? Is anything in solution? No, so don't touch it, just balance it, right? So what do I need to balance it? Here, 5, so always start with your carbon, then go to your hydrogen, and then total, I need 8, right? So it's 16 oxygen, so there's 8. So beautiful, we got our balanced chemical equation. How would you detect one of the gases formed in the reaction? Which gas do you guys want to focus on trying to detect? Carbon dioxide, Megan? Okay, it's called the hold on, flaming splint test. I was like, what was it called? Flaming splint test, okay? The flaming splint test is where you hold a piece of wooden, like a popsicle stick, catch it on fire, and you insert it into a test tube that is creating a gas. There are 3 possibilities for this, and some of you guys maybe did this Scottish Chem, some of you guys maybe didn't. If the flaming splint extinguishes, it's going to tell us one thing, okay? If the flaming splint ignites, it's going to tell us something else. And if the flaming splint barks, like, makes like a pop sound, we call it hydrogen bark, it's going to be another gas. So which one will extinguish? CO2. Okay? Which type of gas will ignite the flame? Oxygen, because oxygen causes a flame to kind of glow brighter. And then the last gas will be hydrogen. The last gas will it's called a hydrogen bark, but it's diatomic hydrogen, which is flammable, but what happens is when you have an inverted test tube and then the flaming splint encounters the gas, it tries to basically ignite it, but it can't, so it just expands real fast, and in that expansion, it causes a sound to come out of the test tube, which is like a burp, like that. We'll try to do it. Last year I almost caught a balloon on fire, didn't it? So we're gonna have to try that again later. Was that in somebody's class? Okay, yeah. I was like, I don't know what to do. The rubber's burning on top of the dust back there. All right, so in this case, we would definitely do the extinguishing test. Like if the flaming splint extinguishes, it would be producing carbon dioxide. All right, methanol, go. CH3OH, right? So it's the carbon with 3 hydrogens, but the one extra spot that carbon can take on is an OH group instead of another H. Burnt in air, so again, I know you guys probably got this far. All right, balance, what do you got? What you need? 2 where? On the H2O. Okay, so that's 4 H's, 1 carbon, 1 carbon. How many O's over here? 4. So what do I need over here? Say again? I can't put a 2 there technically because that's still 5 because you have this extra over here. So we can play around it. Take a minute and play. Say again? Let's see. Go ahead and try it. You should be able to do it that way, but sometimes you have to revise your balancing. Queen, you got me? 2 on the methanol, okay. And that's a 4. Okay, so after taking a second, you can definitely go back and rebalance that. And then everybody, what's the all ending mean? Alcohol group, right? And the alcohol group is not one that will deliver an H plus, like an acidic solution. That would be something like a carboxylic acid group. Okay, gaseous sulfur trioxide. You guys go ahead and do that one because I don't know that you made it that far. Take 30 seconds to predict that product. got, Christian? For the sulfur trioxide one.
SO3 plus water.
Okay.
Yields sulfur hydroxide.
Okay, so sulfur.
Or S.
Hold on. Did you say H?
SOH.
You're trying to copy number one. Everybody look back at number one. Classify it first as kind of the way we would in a generic sense. This is a wet hydroxide or a wet oxide. Metal oxides plus water make metal hydroxide. So this is a note to for just making sure you're clear. Metal oxides and water make metal hydroxides, aka make bases. So we have to have the opposite effect when we have non-metal oxides. So instead of making a base, we're going to make an acid. Good. So sulfur trioxide and water makes. Try again. Somebody else try. HSO4, I think we have to have, right? Because it'd be 3 or 4 O's. Yeah. H2SO4 is what you meant? Gotcha. Sulfuric acid. Thank you. All right. So we're taking our our SO3. The extra O comes in. The 2 H's come in the front. We make sulfuric acid. And then in terms of what the pH would be, you guys can tell me. It would be acidic, right? So acidic would be pH less than 7. They wouldn't specifically ask like where less than 7. We know that's a strong acid, so it'd probably be closer to 1 or 2, but definitely just less than 7 is how we could phrase that. Okay. One thing though we might need to consider, since it's a strong acid and they're aqueous, because we have the ability to put a gas and a liquid together, which could definitely make a solution. How would I write the NIE here? What would change? Any takers? William, what would change? How would you modify this to write the NIE? Good. So this stays the same, right? This stays the same, and then we make what?
H. Or 2H.
1 plus, I got you. I'm going to keep just 1 for now. Okay, because remember this does 1 H at a time in terms of how it dissociates or ionizes. So H, and then what else? Bisulfate, is that what you said? So the 1H sticks with the SO4 and single deprotonization stuff. And then if it were to happen again, I could go ahead and put 2 H's in the SO4 2 minus. But sometimes, like they'll usually take both. But I just want to make sure you guys are clear with that. Only ionizes 1 H at a time. Okay. All right. Next one, similar to number 1. So actually, I'm gonna skip down for a minute. Go down to. Let's go to. Let's go to, there's so many good ones. Oh, there's some repetitive ones though. Ooh, let's go to 19. Okay, 19. Let's see if you can do this one. So it says, I think, solid calcium oxide plus what? Tetraphosphorus dicoxide. Okay, so what's solid calcium oxide? 19, okay, CaO, solid, right? What's tetraphosphorus dicoxide? P what? P4, O10, okay? And it says this is solid too, correct? Does it say something about a catalyst in question 19? It says what? I still can't understand your mumbles. One day. Oh, it just says it's heated. I heard you. Now I understand the bubbles. So you put a triangle on the top of it's heated, and then you got 30 seconds to think of the person next to you, think about what that could make. Don't be too creative, but try to think what it could come to be. I'll give you a hint, it makes an ionic compound, and like a single ionic compound. I'm hearing some things though. All right, 3, 2, 1, pause. Raise your hand if you think you got it. JT. Well, you raise your hand. Go ahead. It's okay if you're wrong. I'd rather you try. Calcium phosphate. Calcium. The single metal has to be the cation. It has to be in the front, okay? And then put all this junk together. Well, there's nothing else you know that has P's and O's in it except for what? Phosphate. So CaPO4. What comes over here? 2 comes over here. 3, balance. Take a second and balance. All right, what goes in the front? Or in the back, I mean, where you guys want to start? Six, okay, 6, 1, 2, done. Okay. All right, so I wanted to give you guys a chance to look at some more NIEs that were not solution-based, because the 9 NIEs, or 9 solutions lab, was 36 aqueous solutions, right? I think you've had enough of those, but of course, go back and practice where you can. I'm going to keep trying to do a couple that are non-aqueous to give you a chance to see how those NIEs are just with reactions, okay? So, flip and notes. You guys have your titration graphs that you need to make, and we're going to talk about our lab that we're going to be starting tomorrow. But I'm going to give you guys about 5 to 10 minutes right now to get your graphs sketched. Okay, so you have paper that you guys can use for writing over here. I will put the timer on. I will try to show you it so that you can pay attention on time. You guys have your graphs. Get your graphs sketched. Let's go. Ready to sketch? Ready to sketch?
Why did you take the chart? Why did you take the chart?
Okay, I can sketch more. And I'm still
Yeah.
For the milliliter one, I got 0.
Yeah. So then how do you find the pH from this? Because these are both run out, right? So the base and the acid run out. So the only thing left is the salt and water. Water auto-ionizes. Remember that from Friday I had like it on the board. So what concentration of H plus does water make?
It would just, what, I use this number?
No, because it actually, it's a constant, and it doesn't matter how much water, how little water you have, it's one concentration always makes. Did you write it down? Give your notes?
Yeah, I have it.
So, yeah, right here. Hydroxide, no matter which way you go, this is equal to 1 so take that. And then see this, the only reason you're doing that is this oxygen and this is moving out, they go from that same time, so you focus on water. So you have your acid up here, your acid up here, that's why you're doing Right, somebody needs to start sketching the graph, like, get some axes on there.
That is my doing. I will take credit for that. I need one. Should be cool.
Guys, your graphs don't have to be perfect. Label your coordinates. Put your names on it.
That's why I said don't check. Whole graph.
So for
Okay, take a couple more minutes and then we're wrapping up to get Alright guys, I need you to take one more minute where you are. You guys can leave those so then you guys can come back for intervention. Okay? You're taking one more minute. We're rolling. I feel like your math is
I did. I was looking at yours.
Okay, guys, come back up here in 3. Drop your stuff.
2. Grab a laptop on your way back. Leave your stuff. 1. Grab your laptop on your way back. Grab your laptop on your way back. 1. Grab your laptop now. Just a quick video. Alright, and wonderful. I will have you guys finish those for like 5 minutes during intervention. I was going to try to do our solutions lab we didn't do during intervention. I don't know if we're going to get to that, but I really want you guys to have a solution. I'll get my priorities straight one day. Okay. So, as I was looking through the test, like the multiple choice side of things on your creating your Unit 2 test, there was one thing I just want to be very clear on, and we don't do a lab regarding conductivity, like comparative across different types of solutions. So I found this quick 1 minute 30-second video. I think it would behoove you to write down some details here. I'll write down some details as well on the board, but we're going to watch this crazy guy talk about solutions for like a minute and a half. You ready? All right, I'm getting your laptop up because we're getting ready to get back in the lab, maybe in like 10 minutes. So just kind of get logged on and stuff and just leave it there in front of you. Okie dokie. All right, so I would just add this to like notes to study for test. And then I want you guys to talk to me about these as he goes. All right, so I told you he's a little nuts. So he's getting real excited about conductivity. I'll wait for everybody to get back there. So as he goes, I want you guys to think in 3 terms. Strong electrolyte, weak electrolyte, or non-electrolyte. Okay? Strong, weak, non. All right, I'm going to go. Is that okay? Okay.
Oh, hi. Today we're going to learn about solutions and how they conduct electricity or don't.
Sounds like something's about to go down, guys. Okay. Tap water.
Tap water.
All right, so what do you say? I told you strong, weak, or non. No. Sorry, comparatively, that light bulb was not very bright. It was dim. Okay, so what do you say? Weak electrolyte. That's because in tap water, there are fluoride ions and chloride ions and other ions that are there, but in very minute quantities. Because why do we need fluoride in our water? For teeth. To prevent cavities, right? So we need calcium chloride to precipitate on our teeth so we don't get cavities. And other chlorides are there just for like a chlorine agent to clean so there's no bacteria causing bad things to happen to us.
Distilled water.
Distilled water. What happens? Oh, sorry. He's so fast. He's so fast. Okay. So you said GI water was what? A non-electrolyte, because what have I done to the water like in our labs? Say again? I removed all the trace elements and all the trace ions, so it's called DI, like distilled water, also known as deionized water, so it's going to be a non.
Water, 1 teaspoon per cup.
Ooh, strong.
Hydrochloric acid. Nice.
Strong.
Sodium hydroxide. Just as concentrated. Sugar water. Sweet.
Oh, hold on. Told you he's crazy.
Sweet.
Hold on. I'm going to keep replaying it.
Sugar water.
Okay, I'm going to pause there. So we went, sweet. Okay. Sodium chloride, hydrochloric acid, and sodium hydroxide were all strong. Why are they strong? They're strong electrolytes. Sorry, I didn't mean to say strong. They're strong electrolytes. I'm not going to write that word every time. Okay, okay. So they're strong electrolytes because they're all what? Strong acids, strong bases, and soluble salts, which mean they not only ionize, but okay, dissociate, but like to what extent? 100% dissociation or ionization. Okay. DI water just doesn't have anything in it. Tap water just has some trace ions in it. And then he said, what did he say was sugar? Sugar, which we know is sucrose. And what happened here? Non-electrolyte. Why? Okay, so it dissolves, but it doesn't dissociate or ionize, okay? So you just get surrounded by water, which is why we can taste it, but we don't detect any conductivity because there's no ions there. Get ready.
Sweet.
Vinegar.
Vinegar or weak acid.
What do you guys see?
Ethanol.
Sorry. Okay. So not ethanol. Acetic acid. HC2H3O2 is vinegar. What happened here? Weak electrolyte, and that's because it's a weak acid which only has a partial ionization. Just partial. We're not going to even put a percent on that. What do you guys predict for ethanol? Yeah, okay, give me a thumbs up if it's strong. This way. Perpendicular if it's weak, and then a thumbs down if it's non-electrolytic. Alright, only time will tell. Okay.
A dissociative that doesn't dissociate.
So that means what? Not electrolytic. So ethanol. What's the formula for ethanol? C2H. Hold on. H5. So that's 2 C's with 5 H's surrounding them. And what's on the end? OH. We like to write the functional group on the end. Okay. So that is a non-electrolyte because it doesn't dissociate. Okay. And that's it.
Don't try this at home.
Oh, I forgot.
Natrium sulfate. It's insoluble. No conductivity here.
Okay, so he's a barium sulfate solution. You saw it was white, right? Did you see it was white? Why is it white? Because there's little tiny particulates that are floating around in there because of their insoluble character. So it doesn't make ions? No. Okay. But, note to self, let's see here. How could I phrase this? I'll do that later because I'm not going to waste time. Okay.
No conductivity here.
Alright, so, and he's from Harvard. I thought that was pretty funny. Okay, so, and I have one more video, which I think I have time to play. Use your functional groups, okay? I'm just going to speed this up just a hair. Just a hair. Okay.
In this introduction to organic chemistry, you will learn the definition of a hydrocarbon and how functional groups give molecules similar properties. Organic chemistry is the study of carbon compounds. There are many millions of organic compounds that you can make using hydrogen and carbon and arranging them in different ways. Hydrocarbons are defined as compounds made of hydrogen and carbon only. The simplest hydrocarbon is methane. It consists of one carbon with 4 covalent bonds to hydrogen atoms. The next in the series has 2 carbon atoms, and this is called ethane, and is followed by propane and then butane, these being the names of the first 4 in the series of molecules called the alkanes. Pause this video now and try to draw the structure of hexane. Hexane has 6 carbon atoms. Here is the structure of hexane. Compare it to the structure you drew. Did you get it right?
Yeah.
The next series is called the alkenes. These are hydrocarbons that contain a double covalent bond between 2 carbon atoms in the molecule. Just like the alkenes, each carbon atom still needs 4 bonds, but has 2 bonds already due to the double covalent bond with the other carbon atoms. The ethene molecule is completed by 2 more bonds with 2 hydrogen atoms for each of the carbon atoms. These also follow a pattern, and the next molecule in the series is propene and then butene. Pause this video now and try to draw the structure of hexene. As before, hexene has 6 carbon atoms. Here is the structure of hexene. This time there is a double bond because it's an alkene.
That's one hexene. This is our first one, right?
The video tutorial on the alkanes and alkenes will give you more in-depth knowledge on the bonding and structure of these series of molecules. As we have already discussed, hydrocarbons are molecules containing only carbon and hydrogen atoms. However, the study of organic chemistry includes any molecule with a carbon backbone. Functional groups are groups of atoms which give molecules similar properties. There are many different functional groups. You may have heard of the alcohol group. This is a hydroxyl group and is a hydrogen bonded to an oxygen, which is then covalently bonded to the rest of the molecule. This group can be attached to any of the alkanes to form alcohols, their name all ending in -ol. For example, methanol, ethanol, and propanol. Pause this video now and try to work out the name of this molecule.
What's the name?
There are 4 carbon atoms in this molecule with an alcohol group, and so its name is butanol.
Right, 4 carbons is a
The alcohol functional group means that all these compounds will react in a similar way and will have similar properties. Carboxylic acids are another example of a functional group. This is the functional group for a carboxylic acid and gives an organic molecule the name oic acid,
Oic acid.
methanoic acid, ethanoic acid, propanoic acid, and butanoic acid. There are lots more functional groups. Esters, which give molecules a sweet smell and make them useful for perfumes and flavorings.
Pineapple ester.
Ketones, which make molecules useful as solvents. Amines, which can be used as dyes and useful in making medicines. Some molecules have more than one functional group and give molecules different properties still.
These get really complex.
Now, by the end of this video, you should know that organic chemistry is the study of carbon-based molecules, and that hydrocarbons are...
Okay, so I think you get the point there, but I want to make sure that you could see a molecule and quickly understand 4 carbons is but and so forth, and we're going to keep going through functional groups as we can. Okay, we get the lights back on for me? Do you mind? Okay. So, pull out your packet. Pull out your packet.
And towards the end, actually, it was a separate document, but
It's called Investigation 4. Investigation 4. And everybody go to my website under homework. Not right here, just- Investigation 4. Alright, so it says, how much acid is in fruit juice and soft drinks? Okay, note to self before we move on. I have got to go to the store tonight to get materials for this lab. Because you're selecting some fruit juices or soft drinks or one of each. And I'm going to try to get a consensus of what I need to buy because I have to use your AP Chem fund, so I don't want to get a drink for everybody. We're going to try to collectively choose here too. So that's one thought, just keep in the back of your mind. And whatever extras I will let you guys have. I don't think I need them for any other lab. Okay, so I'll make sure we don't contaminate them. So if you desire them afterwards, you can have them. Okay. But what we're going to do is we're going to do our investigation. But the first part of the investigation, like we did in the past, it was like a teacher-directed lab. I am not going to teach you how to do titration because we have done one already in class. I'm not going to waste your time reteaching how to do titration. What you guys are going to do is you're going to design your own titration for a specific purpose. But, you know, CJ's purpose might be different than Jaden's purpose because you guys are going to select your own questions regarding that title. Okay, so let me give you a quick preview of what we're going to do. Whenever we're doing our titration, before I move on from here, these are my notes to remind myself to do something for you guys. Whenever we're doing our titrations, we went through this already, but I can have a strong combo, like strong acid, strong base. I can have a weak acid, strong base, or I can have a strong acid, weak base. The equivalence point will change based on the strength of these acids and bases. Where will the equivalence point approximately be if it's a strong base, strong acid? Say again? pH of 7. We can't say neutral because neutral just means that it's somewhat neutralized, not a specific pH necessarily. Where will a strong acid, strong base end its equivalence point? Greater than 7? So above pH 7, because the strong base will pull the pH higher. And then what about strong acid, weak base? Below pH 7. Okay? So knowing those will help us choose appropriately the indicators we select to use during the lab. So what you'll have to do is incorporating your indicator, if that's what you desire for this particular lab, you have to look up where they change color. If they change color at pH 4, where would that be good to use that indicator? Which type? 1, 2, or 3? 3, right? If it changes pH, changes color at pH 9, which type of titration would I use that one for? For the second one here, weak acid, strong base. So we'll selectively use those. And then, other than that, I'll tell you guys about the design part of this. Okay? So, here's your kind of thought, the the purpose behind it. Okay, so you're going to design an acid-base titration, determine the acid concentration of fruit juice or carbonated beverage. So everybody's going to have to do that piece there, determine the acid concentration. But who knows what acids are in fruit juices and sodas? Maybe carbonic acid, right, if it's carbonated. Okay, any other acids that you guys can think of? Say again? Citric acid comes from things that are citrus in nature. All right, so you got some research to do, right? So some of these will be different based on the juices or the sodas that you choose. You're going to do that based on a standardized solution. What does that mean? It's the known. Like, I'm going to tell you this is 0.2 molar sodium hydroxide or 0.5 molar sodium hydroxide, but I'll give you guys a variety of them, so not every group's using the same exact standard. And you're going to do your reaction to make prediction about the acid content in certain beverages, and then the benefit or maybe the detriment it could cause your health. So there's three main connections: acid-base titrations, the different forms of acids in these select beverages, and then how does that relate to health. Okay, so that's kind of what when you guys read this, you'll see that too. This is the part I said we're not doing. So when it says like teacher directed, and it says take this much acid and put it in this much base, that is a mini titration. We know how to do this at this point, so we're not doing that section. But whenever you guys get back in your groups, I'll tell you guys you're going to move on to the part that says pre-lab. So pull out, I'm going to keep borrowing yours for a second. On that document that you guys have pulled out, you guys have your reading first, right? Little pre-lab reading. And it says pre-lab guiding questions. Going through question 9. Okay, do you guys see that? Through question 9. Those are some pre-lab questions. Explanation to strengthen student understanding, that's always a good part, especially to include in your purpose. Your materials that you're allowed to use for your lab after you kind of design what you're going to design. And then do you see where it says in the very bottom left corner, practice with instrumentation and procedure? We are not doing that section because it is a teacher-directed side of things. So you can actually skip reading that unless you need some help with learning how to watch for color change. But down at question 6, you see question or step 6, it says animations, simulations, virtual acid-base titrations. I've updated these links because some of them are dead links now, and I'll show you where that is on my website. You do need to do one of the simulations, and I'll tell you which one. And then after that is a little bit more reading on in terms of procedure. It doesn't give you the exact procedure, but it gives you some steps to include that might be helpful for answering some of the questions that they design here. And then you can see the rest of it's like conclusion steps. Okay. So the one pre-lab link I definitely want you to look at is I think it's the one that says Chem Tunes. Do you see it on there? I think it's the one I've starred. I have this really big on a Google Doc for you guys. You see the Chem Tunes one? Yay or nay? Yes? Okay. I have this typed up for you guys like here. So forgive some of the text when it transfers in. It like makes big letters and small letters, so I didn't type that like that. Just beware. So when you scroll down to the part where it says step 6, which is the part that I specifically want you guys to look at, I've included some other links, but the one on the bottom down here that's in purple says if do a particulate view of this, because the Chem Tunes one actually shows you what that looks like. Okay, and then after that, I give you some tips on what you can and can't do in your procedure. So in this box right here, I tell you some of your limitations, because you guys can make any procedure you want to, but you follow the restrictions. Like you can't have more than 100 mils of your drink, your beverage, your analyte solution. Mainly because I want you to think micro scale, so we don't have any external waste that we need to be contributing to the non-green chemistry side of things. 5 points at which you're going to measure your pH, so tell me the volumes at which you're going to do that. And then you're going to be able to use a pH probe. The pH probes I'll show you guys how to use tomorrow though. Okay, so I've given you kind of the introduction. I want you guys to get in these groups. I'm going to stop choosing your groups eventually, but I'm trying to get you guys to know a couple more people. So I think you guys can see that now. I think Miriam and Cassie, oh, okay, so we'll include them both. I think Cassie will be back at intervention, okay? So make sure you add them on your Google Docs, okay? So Google Doc it up, go. You need to start doing your pre-lab stuff and then start designing your procedure. Pre-lab stuff and design your procedure. You guys can sit at the desk if you want to, it's fine. You can sit at the lab, sit wherever you need to. So anytime it's an inquiry lab and you design online, the whole thing is online. Okay? Keep all of your stuff for that online. You will need to sit and read some first, though. Read. You guys can sit down. I mean, it's